I'm Eli Wintersheet, and this is Lab 2, Falling Object. This lab focuses on the movement of a falling object, and the experiment consists of comparing the motion of a falling object, analyzed in Tracker, to two models, one considering drag and one not, and this can be done using the formulas found on the next slide. These are the drag model, when drag is proportional to the square of the velocity update formula, and the position update formula. In this experiment, the falling object was a rat cap. The video that was analyzed was shot using an iPhone X slow-mo setting, which is 240 frames per second at 1080p for clarity. And the initial velocity found using Tracker was 0 meters per second, and the time between start and finish was 0.595 seconds. And the mass of the rat cap is approximately 0.71 kilograms. If you direct your attention to the bottom left-hand corner of the screen, you can see the video that was analyzed in Tracker. Here you can see my reference length, which is the length of my forearm, and my coordinate axis, which starts right where the bill of the hat starts and ends where the bill of the hat ends, because most of the mass is centered right on the bill. And you can see that the graph found using Tracker has a nice concave. Now if you direct your attention to the top left corner of the screen, you can see the first model that was used. This is the one without drag. So we can see that the initial position is the same as what was in Tracker. G is 9.8 meters per second squared. Time is the same. We describe the weight force here. And then this is what drives the formula. We have the velocity update formula and the position update formula. So when we run this, we see the ball drops just like in here, and we get a nice concave, which looks fairly similar to what we have in Tracker. However, when these two graphs are plotted on top of each other, we see that they don't match up at all. And the reason for this is drag. Now if you look back at Glowscript, you can see this is the script that has drag accounted for. And now this is pretty much exactly the same with just a few key differences. The drag constant is defined as 0.06, and the drag force is also defined using the same function in the previous slides. Now when we run it, we can see that drag has an arrow, and the curve is slightly less concave than the one previous seen. Now when we plot this on top of our experimental data, it lines up pretty much all the way through. This error can be accounted to Tracker, of course. Now one of the main questions of this lab is which of these two scripts would have a terminal velocity? And the answer to this is, of course, the one with drag, because terminal velocity is when the drag force has the same magnitude as the weight force, meaning that F net equals 0. And you can sort of see this, well, in the velocity time graph. This is the one with drag. It's sloping down and will eventually become just a straight line. In the original one, it is just a diagonal, and it will always stay a diagonal because there's no force opposing gravity. The second key question of this lab is, what if the initial velocity is not 0? Like if we had thrown the hat down. And now you can see I've made one change, and that's putting the initial velocity as -5 in the y direction. So when we run it, we can see that there's initial throw in there, and the velocity versus time graph looks very different. It starts at -5, and it looks pretty much inverted from what we originally had. However, it's still going to go to the same terminal velocity because the velocity update formula is still working. It just takes a little longer to get there. Thank you for watching.